A very warm good morning to our resource person, respected faculty members, and dear online and offline participants. Our resource person, Dr. Nirmala Devi, has already joined. So I welcome you, ma'am. So without any delay, we are going to start our session. And before starting the session, we just want to briefly introduce Dr. Nirmala Devi, Madam. Dr. Nirmala Devi is currently associated with DONA International Institute of Assam as principal. Previously, she held the position of assistant professor senior in chemistry, Central Institute of, earlier it was plastic, now it is Petrochemical, Central Institute of Petrochemicals Engineering and Technology, Jaipur, Rajasthan. Assistant Professor in Chemistry, National Institute of Technology, Nagaland. She is the Adjunct Instructor of Chemistry in Huston-Tillotson University, Austin, US. Full Scientist of CSIR at Indian Institute of Technology, Guwahati. UGC Dr. D.S. Kothari, Postdoctoral Fellow at Guwahati University. She had received different professional recognitions and awards from different bodies and organizations. Some of them are National Award for Technology Innovation by the Ministry of Chemicals and Fertilizers, Government of India, Young Scientist Award by the International Academy of Physical Sciences, Women Scientist Award by the Department of Science and Technology. She had number of peer-reviewed international journal and book publication, and she had 5 numbers of book chapters also. She is associated with different professional bodies. Some of them are American Chemical Society, Asian Polymer Association, Indian Science Congress Association, Electron Microscope Society of India. So with this brief introduction, I welcome Dr. Nirmala Devi, Madam, for the session, and over to you, ma'am.
Thank you, Dr. Jitika, for your nice introduction. So let me start today's session. So our topic was, I hope the participants are from institutions, assistant or associate professional, as well as last year of engineering graduates. So let's topic was plastic material present future. Is it visible to you and audible? Everything is okay?
Yes, ma'am. You're audible.
Yes. Thank you so much. So let me start it. So plastic materials, past, present, and future. So we will have some overview of plastic materials in this lecture. So I will try to explain initially about the history and a little bit of plastic materials, how it started, and till date, how they are working, these beautiful and wonderful materials, and the opportunities, the challenges lying in these materials, and as well as about some of the research works that we are doing in our laboratory. So I will also speak some of the few basic things as well as have some chemistry basic fun. So this was the first slide. Mostly I show this slide. I think you participants, do you know what is this? Just to warm up, do you know what is this? These are all spider web. So orb spider made by orb spider. So these I have shown this one because two reasons. First one is that these are the materials which are nature's very wonderful material. They have very high strength, very good flexibility, some adhesiveness to catch the prey for the spider, and as well as the other one, the most important property is their recyclability. So for a spider, every day where they get that, do you know where they get the protein? Because these all are protein. So for a spider, where a spider gets this much of protein every day, because all of you know, I think this a orb spider, they always makes every day, they makes this kind of webs every day. Even we clean today, tomorrow we'll see in the same place or in the somewhere other, they are producing these webs. So do you know every day where they get this much of protein to make these webs? Any idea? Just some guess. So they recycles every day. They recycles it every day. The whatever they eat, like 1/3, 3/3 of no, 3/4 of this material is recycled every day, and other one part it gets from outside or whatever it like eats or whatever it takes as a food, and other it recycles the material, the web, every day. So these are the most beautiful materials world till today produced by nature. So see, they have also enough strength. If we say where is about strength about plastic, like can you compare the property of these materials of this like just waste material? No, can you compare the properties of these materials with synthetic plastics? Yes, it is better than synthetic plastics in most of the cases. See, compare it. So it's lighter than cotton. We know it's lighter than cotton, and you're stronger than steel, thinner than your human hair, but handles loads of hundreds of times of its size. So it's thinner, it is stronger than steel, it can be woven into elaborate structures by minute arthropods that you know. But the thing is that the legions of chemists, material scientists, polymer scientists, plastic engineers are trying to mimic it, the recyclability, the property, the good properties within it. And along with the recyclability, they are trying to mimic, but still it is in the research stage only. We human beings are not able to make these kind of materials, these kind of perfect materials. So let us go through some of the attempts that people are doing. And going to the next slide, you can see here just explaining this spider web. We can compare, I said that how can you compare with this, the synthetic plastics, these materials with synthetic plastics. These are your Kevlar, one of the toughest material, one of the strongest material that we humankind has produced till date. So this is Kevlar. If we compare the Kevlar with these materials, this spider deadline silk, you see strength rating 1.1 gigapascal, not as strong as Kevlar, as Kevlar has 3.6 gigapascal, but tougher than Kevlar. You can see the toughness property, it is tougher than Kevlar. So rigid spider silk is a toughness factor of 180 megajoules per meter compared to your Kevlar's toughness that we already found by our testing and analysis studies. Now you see, talking about or going back to production, use, and fate of all plastics ever made. So do you have any idea that how much plastic still today it is made? How much plastic? It is, we estimate that, this is a recent paper around 4 or 5 years back, which is published in Science Advances. So we estimate that 8,300 million metric tons, not metric tons, million metric ton. Empties for that one. So we estimate that 8,300 million metric tons of virgin plastics have been produced to date. So to date means here it is mentioned up to 2015. The paper is of 2017, and up to 2015, 8,300 million metric tons of virgin plastics were produced. And do you know how much it is recycled and how much it remains in the environment? Approximately 6,300 million metric tons of plastic waste has been generated, only around 9% of which has been recycled. Only 9% of the plastics that we have prepared has been recycled, and 12% was incinerated. You know about incineration, I think, just burning, and then 79% was accumulated in the landfills. How much? 79% of plastics that we have ever made are accumulating in our landfills or our natural environment. So if current production and waste management trends continue, if this trend continues, then roughly, what is the estimate? 12,000 million metric tons of plastic will be going to the landfills by 2015. 12,000 million metric tons of plastics waste will be going to the landfills by 2015. Just imagine how much plastic will be going to the landfill. Will it be a land or will it be a plastic land? Will it be a soil or will it be a plastic land? It will be like that. So the thinking about the plastic is needed. Though there are lots of good and wonderful properties about plastics, so rethinking about it is needed. The concern is always there. What we are doing is really useful or it is just a toxic love story with the plastics. That's why in the recent your book, Plastic, A Toxic Love Story, written by your Susan Frankel, she has said. So she has compared all the plastics with different things, and also she's researched on the history about plastics and written this book, beautiful book. You can see here, this is a P is for your, she has also given a wonderful description about how they are useful, how they entered in our everyday life. But still, there's a question. She has asked question finally. Is it a toxic love story? Because you see, this is plastic chair made of plastics, then your comb, then the third one, the A is for your lighter, then polyethylene bags, IV bags, bottles and caps. So all these are entered in our everyday life. We cannot get rid of that, or we cannot go out of that. But rethinking is always required. Are these materials should be used in this amount, or can we recycle them, or can we make a plastic which are recyclable or as beautiful as the spider silk? So all these questions arise while we're going through the plastics. So the history, the brief history, we all know. Still, just let us have some revision about the brief history of plastics. So it started from celluloid to toxic love story that I have already said. So it started from that, we know long back, there was ivory in our, it is just 1800. We see there ivory was there. This is elephant teeth, we know. Ivory that was used for making combs, teeth, and all these kind of things, or making some jewelry products, rings and combs. Specifically for combing the hair, ivory was used. For tough material, as a tough material, this was the only material compared to other materials, like better properties, which is better properties compared to other materials. But the thing is that US EPA that time also, there are lots of like generation of environmental concern, or the concern about the animals, or killing or utilizing the animal parts or the organ of the animals. Is it sensible decision for the humankind that we are utilizing that one, or the human organ as a material for our use. So that was the question and concern about the animal was arising that time. And that time the replacement of ivory, people were searching for the replacement of ivory, any material that has similar or better properties than the ivory. And that time your medicines company, like your company has your in Hyatt, no, we know, like John Wesley Hyatt, he discovered this one for what? He discovered a material for the munitions company was there, and they declared $1,000 price for making a material which will have property as same as ivory or better than the ivory. So a synthetic material which has property compared to can be compared to ivory. So in response to this, that advertisement, to get a price of $1,000, John Wesley Hyatt in 1868, he discovered one material that was made from what he did. He reacted cellulose. We already know cellulose fiber was utilized. So cellulose with nitric acid, and he got nitrocellulose. That was called gun cotton. Then your nitrocellulose was reacted with camphor. We all know easily available material. Then he got celluloid. So that was the material. Though we call it a plastic, but still it is not a purely 100% synthetic plastic, because he used cellulose as a material. Like a biomaterial, he also used the cellulose as one of the component. So that's why it was partially, it was not fully synthetic plastic. But thing is that its property was very good. It can, this billiard balls that were so hard that can be replaced by, or the property of this was like similar to your ivory. It is very good, good strength, highly like high strength, very good properties, and compared to it can be compared to the ivory. The latter thing is that it has revolutionized the motion picture, the photographic film industry, or you can say that industry is currently called your celluloid industry. The name comes from this word, celluloid industry. We know that time there were like glass plates was used. So glass plates has very good property, but they had one very bad property, that is they are very brittle. They are very brittle, and the heavy weight. Two things were there that have to be handled. One is they are very brittle, and other is heavy weight. Third one is they are not flexible enough. These three things have to be dealt with always. So when it was replaced by this celluloid, this type of material, these three disadvantages were overcome. They can be made flexible enough compared to your glass plates. They are not brittle, okay, and they have not weight like compared to, they have lesser weight compared to the glasses. So all these disadvantages were removed, and it has revolutionized, you know, the Thomas Alva Edison discovered that time motion picture, or your photographic film or glass plate was replaced. So in his invention, there was a lot of contribution of this invention of celluloid by John Wesley Hyatt. So this was the first human-made semi-synthetic plastics. Later again, your 1909, in the similar way, silac was that time used by your silac, you know, it is a gum. It is a natural gum that can be extracted from plant source. So silac was used as a non-conducting material. They were used as a non-conducting material. So this was because that time when electrification was there, and when Thomas Alva Edison, you know, about he discovered the light bulb, and there was tremendous electrification in the US at a time, and a lot of materials which are non-conducting material was required. So that time this was discovered, and like a replacement for silac was searching for, and the silac was replaced by bakelite. Bakelite, we all know, that was like discovered by your Leo Baekeland, and most of our engineering chemistry or polymer science books covers on this bakelite. Like it was developed by your General Bakelite company later, and they have invented 400 patents for its uses and synthesis methods. This material has so wonderful applications and like lots of versatile applications that it is called your material of 1,000 uses. And later this material revolutionized the electrification as an insulating material. That was the good picture. That is, both were discovered to shape the nature, not to destroy the nature or the environment. You can see here, ivory, your celluloid was discovered to replace ivory. Bakelite was discovered to replace silicate. Both were discovered to shape the nature, to save the animals, to save the plants, or for that reason. But today, where we are going, where we are moving, today we have moved to some other worlds that we are not saving the nature, we are not saving the environment, we are killing it, or we are threat to the environment. Am I right? In 1950, it was so popular. This polymer was so popular, like celluloid, cellophane. Later again, like celluloid was not so because nitric acid was used. No, later again, this acid was replaced because it has like a burning or this kind of tendency. So this was replaced, and again, your cellulose acetate was used. So again, your safety film, that is called your, you can also like it's called safety film. So later, lots of history is there where like one material is replaced by other one by adding some better properties. In 1950, these plastics were so popular that in 1950, when they search for three beautiful words, everywhere they does it, the three beautiful words of the decade, 40 to 50, of the 10 years decade in English dictionary or in English language. Do you know what are the three beautiful words? Mother, that you all know, is convincing, memory. Then third one, do you know what was that? Any guess? That was cellophane. Cellophane was the one of the three most beautiful word of 10 years from 1940 to 1950. One of the three most beautiful words. See, what was the popularity of these kind of materials? So going to the recent trends in India, though like people are working or we are working for whatever we can do or whatever we can contribute to this environment or whatever we can do for the better, at least for better. Maybe totally, sometimes it may not be totally recyclable or 100% recyclable, or maybe 100% may not be 100% biodegradable, but people are working, and we hope that in someday some materials will be discovered which will be as efficient as your spider web. So biodegradable plastics, works on biodegradable plastics are going on. There's a huge industry, there's a huge market if anyone can discover a good biodegradable material. First one. Second one, plastic roads. So India has done a lot of things on this. So with an aim to overcome the growing problem of your plastic waste disposal in India. We know about Plastic Man of India, your chemistry professor, Rajagopalam Vasudevan at your engineering college, Chennai, developed the technology to build Indian roads by plastics. So roads made of plastic composites have better weathering resistance than the standard your concrete roads. These roads do not absorb water and have better flexibility. So these are just a glimpse of some of the works that people has done in India. So there were some success story, and one of the success stories I want to share with you, that is your success story of Gujarat. So in Gujarat, there was a success story. It was carried out around 2010 to 2012. So that is called a co-processing of plastics. It is one of the methods in plastic waste management. So co-processing of plastics. What is co-processing? Just let me explain this. I think we'll be understanding. So using of waste plastic materials as an alternate fuel or raw materials in industrial process such as your cement plants is known as co-processing. There is the advantage about this technology is that it can substitute the use of coal and petroleum in industries like the cement plants. In cement plants, coal or petroleum are used as your energy source to run the plants. Now, thing is that these coals can be replaced by plastics, and that plastic is a waste plastic. So where they got the waste plastic? They got the waste plastic from recycled paper-based industries. See, it is a collaborative work. So we need collaboration in this kind of big works or big issues. You see, a collaborative work between your Gujarat Pollution Control Board, GPCB, number one. Number two, your recycled paper-based industries in Gujarat, And number 3, cement industries in Gujarat. These 3 institutions or your industries in Gujarat succeeded in having a scientific solution of utilizing the technology by designing it in a new way. So paper mills got rid of their enormous plastic waste. So recycled paper-based industry, they have enormous plastic waste because plastics are used for coating, coating papers, your cover paper you can see. So plastics are used for coating the papers to make them water resistant. So lots of plastic waste is generated in recycled paper-based industries. So these waste plastics make some lumps that cannot, is removing them or keeping them in somewhere is very difficult. Just like GMC waste or just like food waste, they are also dumped in some ways. So in some field, in soil field. So what they did, so now with this solution, paper mills got rid of their enormous plastic waste generated, and cement plants started utilizing the waste plastics of paper industries, replacing the coal or petroleum. The good news is that in 2012, Gujarat's success story encouraged neighboring Rajasthan to utilize the paper waste plastic-based technology as thermal substitute for cement kits. So once it was the success story was once this success story was spread all over India, then the good news is that it was spreaded in other states also, and Rajasthan, the neighboring country, state Rajasthan, utilized the paper waste plastic-based technology as thermal substitute or the co-processing of plastic technology in their own state too. So this is an example of a circular economy or overall reduction in pollution. So there are other stories are also there. So thing is that the very properties that makes plastics, the unique thing is that the very properties that make plastics so dangerous, is durability and long lifespan also make it get asset. Sometimes it's very dangerous because it remains in the earth for long years, more than 100 years, and sometimes it's a great asset because we can use it as a replacement for wood, as a replacement for animal organs. It has a very good durability, and sometimes the same property which is making it very good material also concerned for the environment. So plastic is such a material that can be constantly recycled. But the good thing is that among this also, there's a good thing that it can be constantly recycled. In some way or this way, most of them can be constantly recycled. This helps the ecology and as well as the economy, especially when the human population is growing rapidly and our lifestyle demands are increasing exponentially. So the solution is not to ban plastic. What we think or what we hope as a plastic material scientist is that the solution is not to ban plastic, but to ensure that it is used responsibly and recycled properly. I have seen that people write like beat plastic pollution, where or ban plastic or beat plastic pollution, where they write in a banner which is made of plastic or resins. The ink they print, that is also a plastic or that is also a polymer. And they write over there what? Beat plastic pollution, or they write it like ban plastic, don't use plastic, like that. And whatever material they are using for that, all are plastics. So think about that, rethink about that. It is a question of concern. It is a question about rethinking how we can do that one. Just speaking lightly like a beat plastic pollution or just ban plastic is not a solution. So whenever till the date whenever when we will not be able to discover a material which is like your worm spider, which is fully recyclable, up to that point it is very difficult to say that ban plastic 100%, because we have to discover that kind of material that can be replaced by IV bags. IV bags जो हम लोग use कर रहे हैं, whatever that like there are so much of materials which are used in drug delivery, which are used in lots of human organs too, like synthetic organs, which are used in everyday life. Lots of things are there which cannot be replaced by plastics these days. So how to replace them? How to replace the ink that we are printing every day? How to replace the printer which is made of, all parts are made of plastic. That class I am taking by a computer, most of the parts of them are made of plastics. How to replace it? The date, whenever there will be some solution, there will be some good solution which is applicable, which should be also applicable, which should be applicable in practical real field. That day only the ban plastic, like ban plastic or 100% banning of plastic will be possible. So people are doing the things, and I'm showing some of the overview, all of them. So what are macromolecules? We all know about macromolecules. So they are very large, big molecules. So larger in solution, just to have an idea only. So larger in solution than 1 nanometer, because the solution is if less than 1 nanometer, then it is true solution. We know in chemistry there are 3 kind of solutions normally we discuss, like true solution, then your colloidal solution, and suspension. So solutions, that is where your particle size is lower than 1 nanometer, they are true solutions, and higher than 1 nanometer and within the range is mostly in, I've given a 1000, but it's mostly in 100. So colloidal size range is 1 to 100 nanometer, and more than that it is called your suspension. So having a molecular weight more than 1000 gram per mole. So the poly and meros, we know all this. So removing 1 or 2 units from a polymer unit does not change the properties of the polymers. There's the one thing. And for your chemicals, for any other chemicals in chemistry, if we remove the 1 unit, there will be nothing. For an alcohol, for an methanol, for an ethanol, if we remove 1 CH3 groups, every property is changed, you know. So what is the difference between methanol and ethanol? Lots of differences. There is differences only your in the as a molecule only CH3 group. In a methanol is CH3OH. Ethanol is CH3CH2OH. Only 1 unit, CH2 units. Only that difference is there, but the property, like lots, all the properties are different. Methanol, it's toxic for human being. It's very toxic, no? Very less percentage can also it's very toxic to human and can lead to death. But for ethanol, we can drink and be happy. So am I right? So a little bit of contamination in ethanol by replacing the methanol can lead to havoc, can lead to death. A little bit, very less percentage can also lead to death. The difference in the molecule as a chemist is only 1 CH2 unit, very less unit. But for polymers, these chemical entities, you remove 1 CH3, 1 CH2, or not 1 or 10 or 12, no property is changing. It will remain same. Because if we can make a polymer of 60,000 molecular weight or a polymer of 60,100 molecular weights, the property will remain almost same. So removing 1 unit or 2 unit is not making any difference in a polymer. That is the most beautiful thing about the polymers and the difference with the other chemicals or other chemical compounds that we are using in everyday life. So there are big 6 polymers. We call them big 6. They're like what are used in abundantly or like very high amount, high volume in our day-to-day life. And they are called in the United States and other countries, they are called big 6. And among the big 6, they're very simple things. Just I'm going roughly like for getting an overview. And among the big 6, one is your polyethylene, LDP, low density polyethylene. So we know that the monomer in LDP and SDP both are polyethylene. Thing is that the intermolecular force, they are holding together because we know it's a long chain. So how they are held together? We know it's a very big chain. So how they are held together? They are held together by your intermolecular forces. So here is some difference. You see, the branching of LDP accounts for its flexibility. There's always some branching in LDP which accounts for its flexibility. Because of what? They cannot, since there's a branching, they cannot tightly get together. So there is always some space between them. They cannot try, like they are like this way, no? So there's a branching in between, so they cannot tightly pack together. So that's why they have low density. So that is the reason they are making low density polyethylene, monomer being the same. Monomer being the same for both of them. It is your ethylene, but the property is different. That I'm saying for the like compared to the chemicals of other chemicals, polymers has these unique properties. Like same monomer unit polyethylene, you are making branching, they are flexible. You are making without branch, they are very hard. So you can use in milk jugs, they are tough. You can use in flexible bottles in your laboratory or in chemical or any other laboratory that we are using as a flexible bottle, no, for water or for keeping the mineral water or flexible bottles that can be used. So it can be a LDP. So it is sometimes it's hard and sometimes it is flexible. So it all depends on the your density, and what depends on density and how density is determined by the branching. So these are the little things that we are going slowly to the plastic world. So in the big six, the third one is PVC, polyvinyl chloride. So what is this? There is only the same ethylene or HDP or LDP we have said. Now one chlorine is added. One chlorine is added. Everything is remaining same. So now what happened? If you add one chlorine, again the properties will be changing, and you can use in lots of ways. They are very hard. They are also very rigid because you can use the plumbing pipe. We are using the plumbing pipe, no? These PVC pipes we know, as well as PVC wire, no? PVC flexible wire. They can be very rigid. They can be very soft form. In both ways, they can be used. These are the very beautiful things. And again, the same things happen here. Another thing will also, there is arrangement one, head to tail to tail, or like a head to tail, or head to head, or tail to tail, or random. There can be lots of, then again your crystallinity, amorphousness comes. Another thing is their plasticizer. I will tell you again about this flexibility. So in your next slide, in the big six, the number 4 is polystyrene PS. Again, the same. The polystyrene used in our CD cases, we are used, which is your crystalline form. We also use them in egg cartoons. There are also like paper-based egg cartons are also used, but they are also available in the market. There are in the Western countries, most of them uses these plastic-based egg cartons, and it is a foamy form, formed plastics. So formed polystyrene. So there can be a foam as well as they can be as a crystalline. Both they can be used, and polystyrene can be puffed by using some vaporizable solvent. They are normally called blowing agent in plastic industry. Using some blowing agent, they can be puffed and make some foam. Common name is styrofoam. We know this allows styrofoam to be very good insulator. So in the big six, the next is polypropylene. Again, we are just adding one. This is a ethylene. We are adding only one CH3 group, but it makes all the difference. Again, it is a little bit harder. It is opaque, tough, and higher melting point than your LDP and HDP, and the utilization is different. We can use it in yogurt. दही का जो container है, we can use it in yogurt container, and resistant to most of the acids and bases compared to LDP or HDP. And in the big six, next one is PET, polyethylene terephthalate. All of you know about this, very common. This PET plastics we know very common, and most of the time they are used in our soft drink bottles. So another one is very not in big six, but very useful, that is Teflon, used as non-sticky coatings. So there are all these polymers can be made. Again, if we change the methods of polymerization, again there is a property or utility of the polymer changes. Most of the time the utility, according to our utility, we are making them. Sometimes we same polymer we can make sometimes as a emulsion coating for paints. For paints, we can use them as emulsion, like a binder, or sometimes we can make them hard polymers. Same styrene, we can make them foam, we can make them crystalline CD, we can use them in paint and surface coatings along with other monomers. So polystyrene, if we use with acrylic acid or like acrylic acid based other monomers, we can again use them in coating also. The same polymer, if we prepare them in different way, in different methods, there are methods of the bulk, solution, suspension, emulsion. These are basic things. I will not go to them. But thing is that same polymer, the just thing I want to tell all of you that the same polymer, again, we make them or we synthesize them in different way. They will be giving different utility and sometimes property too. So how to compute this? These are also basic things, but we again the whole difference is coming sometimes from the molecular weight. The 1 or 2 unit we can change, but if we change the molecular unit from 10,000 to 1,50,000, then again the property will be changing. 1 or 2 unit will not change the property, that we know. But the thing is that same PVC, same polyvinyl alcohol, because most of we know about polyvinyl alcohol, PVA. I have seen in laboratory that in the last year, one of our students from electronics department who was doing PhD in EC department. So what he did, that they came for some, they were searching for some PBA. They came to the chemical laboratory and said me that, madam, give me some PBA that I'll be using for some other purpose in our electronic department. So, okay, this is the PBA. Some students, some of our students that gave them the PBA. Thing is that she got in the paper that PBA is soluble in water, and she tried to solubilize the PBA for 1 week continuously. PBA was not soluble in the water. So what happened? She came to me. What happened here? Thing is that the PBA she was using has high molecular weight PBA. More than 60,000, it was around 1 lakh or it was 90,000 or like that. So high molecular PBA has again different grades. Low molecular weight PBA, medium molecular weight PBA, and high molecular weight PBA. So if we use the high molecular weight PBA, I beat you, you cannot solubilize in 1 week. You can go on styrene, no one can solubilize it. If you take the medium weight, yes, you can solubilize in 2-3 days. But if you have the low molecular weight, you can solubilize quickly within 2 or 3 hours if you go on styrene. So these are the cases. Same PBA, only the molecular weight difference making it different. So these things we have to be take care. So there are some patterns like your low like number average and again in the molecular weights, another thing is there, it is getting slowly complicated. So is the like visually it is very like easy, like easy, we can say they're fun materials. So if you change again, like within the, I've said that how molecular weight changes its property. Now within the molecular weight, again there are 2 or 3 types of molecular weight we normally use. There are your number average molecular weight, your weight average molecular weight, and your what is degree of polymerization. All these are there. So we can compute their molecular weight according to our like degree of polymerization. We all know how much monomer units there. Kitne monomer unit lag rahe? So how much monomer units there? There's a degree of polymerization we all know. So this is a very small like a question, just a review problem. So for fun only, I am giving a single polymer to get a fun only, like a single polymer molecule of STP is found to contain 15,000 ethylene units. What is the mass of the polymer molecule? Just quickly. Anyone? Anyone want to answer? What is the mass of the polymer molecule? A single polymer molecule HDP is found to contain 15,000. How much? 15,000 units. Ethylene is very simple. CH2, is not it? This is very simple. There are 15,000 ethylene units. So what is the mass of the polymer molecule? Just multiply. Any answer? Okay, a single polymer, this was the question. So molar mass of ethylene we know. Molar mass of ethylene is what? How much? 28. Is not it? Carbon is 12, hydrogen 2, 14. Carbon has 12, hydrogen 2, 14. So CH2 means 14, 14, 28. 28 gram per mole. 1 unit has molecular weight how much? 28 gram per mole. So mass of polymer 15,000 units दे दिया है. So 15,000 just multiply 28 by 15,000. How much it comes? 42780 gram per mole. Is it fine? So next one. Calculate the molar mass of polystyrene molecule consisting of 5,000 monomers. If a polystyrene that we are used for CD cases, polystyrene I said, and for foam, if a polystyrene has 50,000 like 5,000 monomers, what will be the molar mass? What will be the molecular weight of the polystyrene molecule? For that, we have to know about the molecular weight of styrene. Am I right? Styrene. Then multiply the styrene by your, what is the molar mass of styrene? This is the styrene, C8H8. There will be some 6-member benzene ring. Then again one more in your upside. Then you just C8H8. This is your molecular composition, the formula. Then what is the molar mass? Molar mass is 104. Carbon we know 12. 12 into 8. Hydrogen 1. So it comes 104 gram per mole. If we multiply this 104, then if we multiply this 104 with how much unit I said? I have said 5,000 monomer units. Multiply it by 5,000. It will come in gram. So if you convert it to kilogram, it will be 520 kg. Am I right? Is it okay? Coming to the next level. I think these all are okay. They are fine because just we are multiplying them only by degree of polymerization. How much monomer unit? Then just multiply the molecular weight. You are getting the molecular weight of the polymer. Third one, a little bit tricky. A very small question, little bit tricky. Engineering first semester, mostly we ask for the engineering chemistry, for the engineering student in the first semester when they go for the chemistry classes. That's like a little bit tricky, but a very simple question. A polymer with a representative formula. What is this? Now it is given CH2 CHSG. SG means side group. This is just a side group. Okay, there is some side group in this polymer. CH2, CH, and then side group. Here's the degree of polymerization. How much? 500. Degree of polymerization, how much? 500. And molecular weight, how much? 26,500. Molecular weight here, 26,500. Degree of polymerization, 500. Identify the monomer. This monomer, can you identify this monomer? CH2, CHSG, some side group is there. Just monomer is almost identified. We just only want to know the side group. Side group, we want to know. So identify the monomer or identify the side group. Do you have any idea? Just take some for 2-3 minutes. Participant, do you have any idea? Just I want to know. You can chat me in chat box too. Just for fun only. These questions are just for fun only. Any idea, any guess, you can discuss. If you have any idea in mind or any guess, you can discuss. So a polymer with a representative formula. What is the representative formula? It is CH2, CH, and SG means side group. One side group is there. Has the degree of polymerization, how much? 500. Degree of polymerization means how much monomer are there. Degree of polymerization means how much monomer are there. No, so degree of polymerization is what? 500. Molecular weight, how much? 26,500. If we divide it, then you will get the monomer molecular weight. Okay, so identify. I have given the clue. If you divide it, you will get the monomer molecular weight. I'm giving clue now. I the SG means I can identify the monomer. So is it okay? So if we divide this 26,500 by 500, what it comes? So how much it comes? So how much it comes? If we divide this 26,500 by 500, then how much it comes? Around? Okay, fine. Slide is not moving. Yes. So thing is that it comes around how much? 26,500 by 500, it comes 53 or what? That means it will be polyacrylonitrile. If it comes 53, 26,500 by 500, how much it comes? Let me calculate. So how much it comes? 26,500. 26,500, you divide it by 500, it is coming 53. That means 53 gram per mole is the molecular weight of this unit, this unit, this monomer, 53. So 53 means what it can be? This is already, we can minus now. This is carbon is 12, this is 2, 14. So from 53, we will subtract this 14, subtract this 13, carbon 12, ye 12, 13. So how much it remains? From 53, if we subtract this minus this 14, no? 39, then minus this 13. How much? 26. Or how much it comes? Then side group will be your carbon and your nitrogen. This is your acrylonitrile. Carbon and nitrogen, CN. Side group is a CN, that it becomes 53. Agar aapne, if we keep it here, carbon, nitrile, CN, it becomes, the whole molecular weight becomes 53. The polymer is polyacrylonitrile, like your monomer is acrylonitrile. So there is a quick, just for understanding only. So let us move in. So rethink all about this question. Just to like warm up only, I was giving all this, throwing these questions and to interact with you. And what makes all the difference in the same polymer? Just I have said that there are like PVC, there are lots of difference. They can be sometimes hard, they can be sometimes very flexible. So again, for polystyrene, they can be sometimes foam, they can be as a hard material, they can be used. So what makes all these differences? For PVC, for polyurethane also, we can make them sometimes foam, and we can make sometimes use them as a shoe sole. We can use them as a shoe sole too. And we can use them as a foam too sometimes. So what makes all the differences? There are 2 or 3 things. One I said molecular weight, other I said about the fashion, the arrangement of monomer chain in a molecule. Okay. Other is one is molecular weight, difference makes them all the difference. Second one is the arrangement of monomer units in a polymer chain, head to tail, tail to head, or your random. Third one is the use of, I have not said, third one is the use of plasticizers. Plasticizers can be added to a polymer to make them flexible. If you want to make them flexible, then we can use plasticizer. If it's very hard, it will become soft and flexible. So the plasticizer is a molecule which can sit between the polymer molecules. Just I said that LDP, STP, when I explained, I said that they, like, this is a polyethylene molecule, they sits like this way. So what binds them? Intermolecular forces binds them. So if you break these intermolecular forces, if you insert some of the plasticizer in between them, what happens? The binding, no? This one, the packing of the molecule is distracted, or it prevents from packing. So that is the role of a plasticizer. If you insert a plasticizer in between them, so it prevents them from packing too closely. So that's the role of plasticizer and makes them flexible. So there is the role. So what is a plasticizer? Plasticizer, they are small molecules. They are not like plastics or polymers. They are not long chain molecules. They are short chain molecules. They are small molecules, and they are added to polymers to prevent them from packing and make them flexible. So that is the plasticizer. So the new car is built. So there was a research in around 2015 or 2017 in University of Texas at Austin. So they said that the new car smell, we got, everyone get the new car smell, no? The new car smell is just a plasticizer smell that is used to make the dashboard and other plastic components in the car. So the new car smell is due to that one. Along sometimes solvent, and most of the time it is due to the plasticizer that are used while making the car dashboards. So about condensation polymers, these are all your addition, condensation we know. there are also some natural polymers which are like we can say them condenser silk, wool, cellulose. So there are lots of condenser polymers are there, polyesters. We will not go them detail, but however, just to have some idea, only polyesters are there. Then the trade name of which is your Dacron, no? So Dacron is a polyester. So it is used for a fiber and clothing. Polyesters, I say it again, polyesters can be used, no? Polyethylene terephthalate, they are also PET. So it is a different property. Then again, PET here you can use sometimes it's a fiber also, or Dacron. That's why it's called Dacron fibers. No, Dacron is also a polyester, and it is used as your fiber for clothing. So if we check your t-shirt, you will see that it's a blend of cotton, natural polymer of cellulose, and a polyester. It is called Dacron. So if we check our t-shirt or our coat, we can see that it is some kind of like some percentage along with some percentage of Dacron. So that is the use of polyester again. Along with the PET bottle, I said, again the see is a fiber like. So again, we can make the same polymer sometimes fiber and sometimes as a film. And sometimes a film. So in both ways, the same polymer can be used if we process them in a different way. Again, the other thing comes out here. What is that? Processing. That's why processing of plastic is so much of important. We'll get different kinds of like properties. So polyamides will show different properties if we process them in different way. So other lots of important polyamides are there. Like nylon. Again, you can be used as a fiber. We can use for socks. Okay, most of the socks are made of nylon. Kevlar, we already know it's different. Like this can be used for a bulletproof vest. It's very tough. So in this way, different kinds of polymers can be used. So there are diversified use of plastics, and sometimes the same plastic can be used in different ways with different properties and with different utilities. So thing is that now the symbols we know already about. For PET, symbol 1 is given. For SDP, symbol 2 is given. They are all recycling numbers for different plastics. So now, where do they go after use? I have already said in the first slide that the disposal is a problem. So most of them goes to the landfill, incineration, and recycling. So recycling amount is very less. You see here, the recycling amount is very less. Most of them go to the around 80% of plastics of this world produced till today goes to the landfill. So municipal solid waste. Just few days back, I also discussed with GMC Commissioner Devashish Sharma, who was a very active and he's working actively in this field. So very active officer in this field. So present GMC Commissioner Devashish Sharma, they are working on this, like how to this municipal solid, how to deal with them. So how to deal with them. So all this, they are also helping the entrepreneurs or startups if they want to utilize their fields or if to utilize their knowledge. They are also helping most of the startups or the entrepreneurs. So thing is that landfilling, incineration, and then recycling. These all three goes. But thing is that how to increase the recycling? That is the question mostly we discuss. So the four things we use here are the source of reduction and reuse, like source reduction, then reuse, then recycling. So we mostly use the 4R principle here: reduce at the point of production where we can reduce, if possible, reduce, if possible, reuse, if we can, then recycle it. If the three are not possible, then try to go for recover. We also recover sometimes the material or the monomer can be recovered. So if we cannot do that one, then we can recover. So we can use, sometimes we can one by one, or we can use all four of them to the same polymer. So these 4R principle we use. And composting, we all know about composting. The most of the municipal waste or other cardboard, natural polymers can be used for composting also. But for synthetics, we generally go for biodegradation. The one new term again, the biodegradation is there. What is biodegradation? It's used for biodegradation is using bacteria or fungi to decompose the polymers. So bacteria or fungi can be used to decompose them. So usually this is not a problem for natural polymers, but bacteria and fungi have no enzymes which can digest man-made polymers. they can usually, like, this is not a problem for natural polymers, but bacteria or fungi have no enzymes which can digest a man-made polymer, that is your synthetics. So what we can do now, we can incorporate some chemical groups into the polymer chain which can be attacked by water. So we can introduce some chemical groups in the polymer chain. The polymer chain is long. If we incorporate some chemical groups, then that can be attacked by water. So this will break the large chains, since the problem is that they have a very large chain, very high molecular weight. So if we break the large chains into smaller ones, which can be dealt with by bacteria and fungi, if we make them very smaller by introducing some chemical groups, then later they can be dealt by the fungi or the bacteria. So that's the thing. So average molecular weight, I have already said about PDI, like number average molecular weight and weight average molecular weight. The third term is, again, one term is there. If we divide the weight average molecular weight by number average molecular weight, we will get again another term, that is your what? Polydispersity index. That also creates some difference in polymer properties. That's the thing. The third property, that what makes difference, I said, what makes difference, one is the arrangement, one is the molecular weight, then again arrangement, then again addition of plasticizer and other additives, then again your polydispersity, the number average and weight average. There are molecular weights are there, lots of molecular weights, like two are most common. Again, viscosity average molecular weight is there. So again, PDI makes some difference. So I will not go for the calculations. However, if we have interest, we can do some calculations, because the people who are in this field, or in the chemical engineering discipline, or in the first year of BTech, people does this kind of they are allowed, students are allowed to do this kind of MN, MW, number average molecular weight, weight average, and PDI. So if anyone has interest, they can like click these questions and like just practice at home. So how to calculate the number average, weight average, and how to do some fun with them. Not only the calculating, this is just a simple formula there for calculating, just we divide them by using the formula. But the thing is that we can also use some of the tricks or this type of questions. A polymer consists of 40% by weight of the macromolecules of molecular weight, this one, 60% by weight of the molecular weight, this one, calculate the number in the weight average. So there are a suspension contains equal masses of particles with molecular weight 20,000 and 40,000. To calculate the number average and weight average molecular weight. So in this way, like different questions, we can sometimes, for practice at home or for having some fun, we can use these questions. Just let me change the slide. Maybe it is getting hang. Let me go to the next slide. It's not moving. Okay. So these are all questions we can, I have also given the answers. If you need, then we can try at home, no problem. Okay, this is a GET question that came in GET. Most of the engineering students, since there are some, like organizers told me that there are some last year, final year students are there, maybe some final year of engineering. So normally in the GET, some questions come like this is small questions. So for a polymer, the number average molecular weight, weight average molecular weight, and viscosity average molecular weight in general obey the following relationship. Which relationship they obey? So which relationship they obey for a polymer? A, B, C, D, which one? Can you just guess? This question came in GATE 2019. Number average, weight average, MB. Mn is greater than MW is greater than MB. This one, MB, A, B, C, D. Any guess which one will be the right answer? Unmute yourself. If anyone is replying, just unmute yourself. Any guess? A, B, C, D? So it is your?
Students are speaking C.
Yes, they are right. C is the right answer. So C is the right answer. So I'm happy to know about you. And the next, because we have understood all the things like overall idea about the polymers. This question was just for warm up, and but these questions, a few like small things comes in get exams, so we can prepare the students in this way also. So we can encourage them how to learn about polymer or how to learn about plastics. And now I will slowly quickly go to some of the works that we are doing in our laboratory. So we are working on wood polymer composites based on waste plastic. Some of the works we are doing on this one, since this class was on plastic based or about how waste plastics. So I will tell you about simple things that we are doing in our laboratory by the works are done. Most of the works are done by our students of BSMS masters in material science students, and they are also doing on some plant oil based resins and surface coatings. So all the things, the thing is that we search for some simple solutions for the big issues, and we try to respect the principles of green chemistry. There are 12 principles of green chemistry. We try to respect the 12 principles of green chemistry. So the baseline data was collected from Sumukujima and NIT Nagaland. So these were the plastic, like neem wood wastes. The waste fiber was collected from wood dust, was collected from the Sumukujima part of Nagaland. You see, they all burn. That means incineration. They don't know where to use them because they are getting some dumped. So they are all mostly they are incinerated and getting dumped there. So we've collected, the student has collected this wood dust, and he tried to make a composite with some waste plastics. Waste plastic he collected from the laboratory itself. So this recycled plastics, wood fiber, and he added some additives. He made some wood polymer composites. So we can see here that recipe was very simple, and he made some wood polymer nano composite using titanium dioxide and then hydrophilic clay, titanium TiO2 he synthesized in the laboratory, and then clay, and then he prepared this kind of plastic like WPCs. You can see here the sample designation was this is polymer blend, and then PBG5 you see here, this is your GMA, your PHR, polyethylene polyethylene grafted glycidyl methacrylate used. Then you can see here the properties are improving, and these are the treatment of wood dust, and the methods is given. The wood dust was treated with 1% sodium hydroxide solution at 60 degrees Celsius for 1 hour. It washed with distilled water, and died, and he got some modified wood. And he also synthesized TiO2 nanoparticles, I said, with salt gel method, which are already established methods are there for synthesizing of your titanium dioxide nanoparticles. So with these already established methods, he prepared TiO2 nanoparticles, and then he used these TiO2 nanoparticles to modify with CTF. So he modified CTF. Then what he found, with that modified TiO2 nanoparticle, he used this your plastics, 3 kind of plastics, your HDP, LDP, all are waste. HDP, LDP, and PP in the ratio 1:1:1. Later he added again PVC was added later, because PVC, I said already, chlorine is there, so it can resist a very high temperature. So PVC is added in the later part. Initially 3 plastics were used, HDP, LDP, and PP 1:1:1. Then later added again your 3 gram of PVC later. So you see with the THF. So all these mixed together, then he got some composite. That composite powder was pressed or processing step now comes out. That powder, nano composite powder with TiO2 and wood dust, where then your composite sheets were obtained by your compression molding press. This is a molding press, and your at 170 degrees Celsius under pressure of 80 megapascal. This is, he pressed it, and then he tested for, these are the pressed, these composite sheets, and he tested it for mechanical properties. How much mechanical property it can give? Is it compared to other polymers, or is it compared to wood? So he then again did some water uptake studies for comparison, and he did some chemical resistance tests and all the tensile, flexural, and all these tests. So it was comparable. So this he was a student. He was Vamsi Nerethi Ratnam. That time he was a master's BSMS master's student in material science, and now he is a officer in some industry. there in Andhra Pradesh. So his work was published in composite science and technology, and you can see here the water applied studies. So this was a simple thing. Then he also did SEM and TM. You can see here the particles like there. These are the TiO2 nanoparticles, and then again the clay, this thin hair type of things you can see here for TM studies. So in this way, all these composites were made. You can see here very good uniform these composite sheets, WPC wood plastic composites made of neem wood dust, waste neem wood dust, as well as waste plastics of laboratory. LDPE, there were four plastics were used. LDPE, like flexible bottles, I said they used from lab. Then again HDPE, and HDPE are commonly used for like chemical containers. We can get them. And then again PVC, this is flexible pipes, I said, or plumbing pipes we can be used. So PVC, and then your HDP, LDP, and then PP, polypropylene, and PVC. These four he used, and he made this kind of composite materials. So later he worked for also for can we make them transparent, because his idea was that if we can make them transparent, then it can be used for some solar applications. So he worked on this, but this work is not completed. Still, he did a lot of work for making them transparent. Making transparent, that too with waste, is very difficult. But it is possible. Making transparent is possible, but still for waste is still difficult because lots of additives are there in the waste plastics. So that's why without removing them, making them transparent is really a difficult task or a challenging one. So he worked on that. So these are the neem seed oil based plants and other works. There's like there was some other students, Marinita, who extracted the neem oil from neem plants, and then that was all based on the earlier part of the work was based on neem wood dust, and these parts are work on neem oil. So she collected neem seeds, she dried, sun-dried the neem seeds, and then what she did, she like extracted the neem oil by using petroleum ether from the crushed neem kernel by using Soxhlet extractor. So solvent removal she did by rotary vacuum evaporator. So the solvent can be reused. So that's why like not much use of the solvent, it can be reused. And the collected solvent was reused. Then extracted oil was purified by column chromatography. Then she also tested it by doing TLC, thin layer chromatography, and the technique was used for confirmation of purification. If it is a purified or not, for confirmation of purification, she used TLC method. And then she studied some physiochemical properties like percentage yield, acid value, iodine value, saponification value, etc. She also did some GCMS studies to see the percentage composition of the neem seed oil, and it was found that your percentage composition of neem seed oil, you see here caprylic acid, myristic acid, palmitic acid, and stearic acid. And then again unsaturated fatty acids are there. This is a percentage unsaturation. That means a very good number of percentage of unsaturation is there. So that's why they can be utilized for synthesis of resins. Since there are some double bonds, we can utilize the double bonds to resinify them. And finally, see like made some resins. We can see here. I'm quickly going to the resins. You can see here the resins synthesized resin ABCD, and all these resins were utilized for doing some like water contact angle measurement and then anti-corrosion studies. The resins she found were used for as a anti-corrosive coating. So that was published in 2021 last year. And she also did some copper oxide nanoparticles synthesized, and she did some catalytic studies or the catalysis or how much the reaction can be enhanced or the like shorten the reaction, like time duration of the reaction can be reduced, and the work was very good. And that was all about, I think we are going ahead of time. So let me going to the final slides about the things. So the question is that how to go to from Millennium Development Goal to the like your sustainable development goals by 2030. So what is the role of a plastic material scientist like us? The role of a plastic material.
You can take 15 minutes.
I can take now 15 minutes.
Yes.
Okay, fine. Okay, fine. So let me go back again a little bit about, I was telling about these corrosion studies. So these materials we can see here, like degree of polymerization, I said. So degree of polymerization was enhanced when we used copper oxide nanoparticles. She did initially from neem oil, she synthesized some polymer, I said, and they can be used for anti-corrosion studies. Then again, see what is it? She did some copper oxide, synthesized some copper oxide nanoparticles in the lab, and with that copper oxide nanoparticles, what she did is that these copper oxide nanoparticles are there. You can see here. These are the TM studies. So these copper oxide nanoparticles and the DLS study shows that the size of the nanoparticles are around 200 nanometer. So you use these copper oxide nanoparticles to synthesize the polymers or as a catalyst, as a co-catalyst, because catalyst was already used. Sodium hydroxide or lead monoxide catalyst was already used. So along with the sodium hydroxide, she used copper oxide nanoparticles as a co-catalyst, and the reaction time was reduced appreciably. We can see here for the resins, you see acid value decreases for resin NR, means like you're without nanoparticle, 100% phthalic. Resin 109, 100% phthalic anhydride, 109 milligram of copper oxide nanoparticle. Resin N219, your 100% phthalic anhydride, that means phthalic anhydride is same, and 219 milligram of copper oxide nanoparticle. That means without copper oxide nanoparticle and with copper oxide nanoparticle increasing. So with increasing the copper oxide nanoparticle, the reaction is become quicker. The reaction time is reduced. We can see here. So you can see, we see also calculated some degree of polymerization using the formula. So C0 is for your acid value at time 0 minutes, CT is for acid value for 180 minutes. You can see here the NR, here NR and 109 and 219. You can see here that the degree of polymerization is increased from 5 to 16 to 20. So degree of polymerization was increased. That means reaction time was reduced appreciably. So again, moving to the next. She also did some FTR studies, and some of the DSC and DTS studies, the properties were very good and it has very good thermal stability. So also did some water contact angle studies. If you go for the water contact angle analysis, if you compare them, then we can see that there's a water contact angle. You can see here neem oil based alkyd resins for A, B, C, T here. You can see resin A, B, C, and T. And this NR and 109, and these are for the initial first resins, A, B, C, D, without copper oxide nanoparticle. These are for ABCD, only changing the maleic anhydride content, phthalic and maleic anhydride composition. So with increasing the maleic anhydride, the water contact angle was increasing to 97 degree. So picked up this one, this resin A was picked up, resin A is same with NR. So it is showing same water contact angle. Now this NR was reacted with, I said already, along with copper, using copper nanoparticle as a co-catalyst. So what I find, the water contact angle increases now again for the same thing NR. If you compare this one, 102. So water contact angle can be increased. That means it has water repellency effect and as well as the anti-corrosion. If you do the corrosion study, we can see here, this is for uncoated panel. Before immersion, they are mild steel plates. So these are the uncoated mild steel plates. This is a paint coated, is coated by Asian paint. And then you see this is coated by the resin synthesized in our laboratory. Then resin 1, like 109, means using the copper oxide nanoparticle, and this is by resin 219 using the higher amount of copper oxide nanoparticle. If you compare after 4th day, you can see there is an uncoated panel getting rusted or getting corroded. You see here, we used, when we use Asian paints, there like bumping is there, no, some swelling or bumping of the paint is there. For the resin synthesized in the laboratory, that is, it shows appreciable very good anti-corrosion properties. Here we can see, and after 6th day was also like appreciable good, because they are, most of them are water repelling. So these studies done by Parinita Das. We also did some of the encapsulation studies in this talk. I will not tell about encapsulation and other things, because we basically focus on the waste and plastic waste and the treatment, or how it can be recycling of the plastics in this talk. So still, like we also encapsulated the neem and all these parts, I am not going to tell here. However, these are all done by polyelectrolyte complexation methods, and you can see here good particles that we have synthesized. This is the last part of our work, and we can also develop some polymer nanoneedles, and like in different way we can change the morphology from the surface morphology or the shape and size of the particles. We can tune them properly, like whatever we want according to our requirement. We can tune them for their size and for their shape, and other properties, we can tune them. So thing is that how to move to now the question is, the Millennium Development Goal was given in your 2000, from 20 to 2015, it was like Millennium Development Goal was there. So most of the, among the goals, there was that like reducing poverty was there, like for working for environment was there. So it has improved a lot. Like some issues were raised, and also we get some solutions, or we get some like there were some improvement of the living condition of the like world human, like most of the people in the world, or though it was not completely like that time, poverty eradication was not completely possible, still sustainable development goals, there are 17 goals in the SDG, and we want to reach that by 2030. So no poverty, zero poverty. And then environment has again concern. There are 6th and 7th, you will get that regarding the environment, reducing the environmental impact, life below water, life underwater, how to protect the life of fish, or the life under, there are lots of like, there's ecosystem underwater in oceans and all. So they are also affected by plastics, microplastics, or the decomposed, or the like disintegrated plastic products, or the plastics that were thrown, used plastics, that is also like which are continuously thrown to the oceans or sea. They are concerned for the lives of the animals, aquatic animals, or plants underwater. So how to tackle with them? This is also one of the sustainable, among the 17 sustainable development goals, there is also one goal, and we have to do some of to contribute to achieve something, to contribute to achieve to these sustainable development goals by 2030. So what is the role of a plastic material and engineer and a polymer chemist in achieving these sustainable development goals? So that is the question, and we think we can utilize the 12 principles of green chemistry, as well as how we can contribute. Still a lot of research is going on, still we need to do a lot of work. If we think it globally and act it locally, I think there is no limit the amount of good one can do if we don't care about who gets the credit. So if we think that one, I said already that in Assam, if we think it is like think globally, act locally, where I said that in Assam, PWMC Plastic Waste Management Center, Guwahati CIPET is doing a lot of things about the like single-use plastics, or they've collected, I've seen in their website that they've collected, and they did a lot of works on waste management, or that center. And I also talked last around 1 month with GMC Commissioner Devashish Sharma. He was a very active officer. I said they are giving training, they are giving a lot of help, people who wants to do, or who wants to locally do something to contribute to the environment, to contribute to the world. They will be helping, or they will provide the resources as well as some official support to help anyone who wish to work in this waste management, because they are focusing this 5 years from last year, he's focusing on how to make Guwahati clean by this plastic, by how to reduce the plastic waste, or how to recycle them in different ways, how to make the city clean. They are using, so plastic is one component of them, and I think he will surely help anyone who is really interested to work on that. And also I talked before around 1 month, Partha Pratim Pathak, he is MD, like Managing Director of Fresh Air Waste Management Services Private Limited, working. He is a national awardee, so he has done a lot of things, tremendous things. He is an engineering graduate from Assam Engineering College, AEC, here just like nearby us in Chalupari. So a fresh engineering graduate, and now he has done around 6 to 8 years of work after being graduation. So he's a very active entrepreneur, and he's working on management sector like biomedical waste. So what they does, they collects the biomedical from different hospitals, from GNRC to from Guwahati Medical College Hospital. They have a close contact with all the hospitals. So from hospitals, they collect the waste, they treat them, and they recycles them. So related to biomedical waste, they have done lots of tremendous works. So it is a very challenging work, as well as there is lots of opportunity. We know that the opportunity is always there where there is some challenge. Without challenge, there will be no opportunity, or there will be that opportunity is not will be as unique. So this area, this plastic waste area, has lots of challenges as well as same amount of opportunities to work. So if we want to contribute, we can work, or we can make contact with them and we can work. So Parthapatim Pathak, he is really a very busy person. So, but anyone, if are interested, they can contact with them, or they can collaborate with them to contribute. So the process of learning, unlearning, and relearning will go on. So that's why I've given this one, that like process of this way, for plastic waste, or for the things like a big subject like a polymer or plastic industry, the learning, unlearning, and relearning will go on. We'll modify, we will develop, or we will work for better. How a good solution or a best solution for the plastic waste management can be checked out. And above all, that I say that we have to stay hungry, stay foolish sometimes to become an entrepreneur or to work on these sectors. I think some solution someday will come out surely. And I wish to acknowledge, I wish to thank SIT Division, DST, Government of India. The first project was was done according, due to their generous funding was there. And CSI New Delhi, then NEC Shillong, Northeastern Council Shillong, then NIT Nagaland, as well as CIPET Jaipur and to Dia. So we hope that greening is possible. And thank you all the listeners. If you have any questions, I'll be happy to discuss with you.
Thank you very much, ma'am. The session is now open for interaction. Online participants can raise their hand if they have any queries, or they can write at the chat box.
Yes, they can write, and I'll be happy to discuss or answer with them.
Ma'am, what is the concept of green chemistry
Yeah.
and environment?
Yes. That is a good question. So this concept was relatively new. Around 1980s, it came, like concept of green chemistry, that it utilizes 12 principles. There are 12 principles of green chemistry are there. So like reducing the waste is also among them. Like when you do the reaction, like utilizing some green solvents like water, or which are non-toxic solvents, this is also one of them. So there are 12 principles of green chemistry are there. So if you go them, like regarding all sustainability, how to make chemistry a benign, or how to make chemistry how to move it from hazardous to some benign chemistry. So there are some 12 principles where they are like reducing solvent, or reducing some good solvent, like better solvent, and then like reducing the number of reactions. Sometimes we do reactions, sometimes we get the product, but we use number of steps. How to reduce the steps, or reducing the step is also reduces some of the chemicals. So how to reduce lower chemicals, how to use the better solvents, which are green. Green means your environmental friendly, eco-friendly solvents. So these there are some principles are developed. So atom economy, because there is also some energy efficiency, atom economy, these things are included in the 12 principles. So then again, reducing toxic byproducts. If we get a good product, yes, we sometimes we get some good products, but thing is that how you are doing the, always there is, if you get the good products, the process you are doing is also matters. That also matters. In what way you are doing the reaction. If you are not doing the reaction in a proper way, or if in the process of getting the brute product, you are eliminating a lots of waste in between the reactions, then it is still not a green chemistry. From green chemistry side, it is not a green reaction. Thing is that that I said, like this is a like chemical we are using, and we are getting some good plastic products or any kind of good products. Answer is fine, but the thing is that a work done by in a bad way, a good work done by in a bad way is also still a bad work. Understand my point? A good work, if you done, the work is good. Okay, a good product achieved by a bad way is also a bad product. So that is the thing. In what way you are doing the reaction, or in what way you are getting the product, that matters the most. So that is the reducing the side products, reducing the other products, reducing the side waste products. So how much chemical you are using, and how much atom economy it is, no? So how much side products or byproducts you are producing, how much waste you are generating, how much energy you are consuming, all these things matters in this case. So thing is that that's why there are 12 principles are already developed by Paul T. Anastas. There's a good book written by Paul T. Anastas, who was a pioneer in this. I met him in Venice, Italy in 2016. I visited there in a IUPAC Clean Chemistry workshop. So Paul T. Anastas, and they came there. I met him personally there. So like they have developed this, Warner and Anastas. So there are good books written by them. So the concept is utilized nowadays in chemistry in everywhere field. The concept is like now it is emerging as well as spreading in every chemistry or laboratory. These people try to utilize these principles, even if they are doing what kind, like any kind of work, will try to apply. If we can apply these principles, if we can, then it is very good, and that things matters. So these are the principles. They are like summarized. There are 12 principles are there, like atom economy, reducing the waste, reducing the side products, increasing the atom economy, increasing the energy efficiency. There are some principles are there.
Thank you very much.
Okay.
Thank you very much for delivering this informative session, focusing from the basic concepts of polymer to the green chemistry, waste management, and how this can be environment friendly. So I, on behalf of CIPET CSTS Guwahati, thank you, ma'am, for spending your valuable time with us. Thank you very much.
Thank you so much. Thank you so much, all the participants and the organizers. So we are grateful, and I'm also happy to deliver the lecture. And even if we are not able to attend personally these days, I think someday we'll be again to attend personally and interact with them. So because sometimes the interaction personally or physically becomes very fruitful. Thank you all, and thank you all the participants.
Yes, we also hope that in next we will be meet you offline.
Yeah. Thank you. Thank you so much. Can I leave now?
Yes, ma'am, you can look.
Thank you so much.
Good morning, dear participants. We are going to start our next session. In the next session, our senior technical person, Mitali Saharoy Madam, will briefly talk about the testing techniques related to different polymer products. And after that, we will go for live demonstration. For the offline participants, we will go for live demonstration. And after lunch break, CIPET CSTS Guwahati has another center, CIPET PWMC Plastic Waste Management Center. So where waste management, a full setup is there. So we will proceed for the visit to the Plastic Waste Management Center, where we will have the live demonstration for the waste management methods and techniques, as well as the process. A very warm good noon to my dear participants, respected faculty members, and technical persons, technical experts, senior technical persons from our testing laboratory. Since CIPET has an NABL accredited laboratory, so all the state-of-the-art testing facilities are available. So we have with us today Mitali Roy and Hoymanti Das Madam. And Mitali Roy Madam will very briefly will speak today on testing and quality control of plastic product, which is one of the most important field for assuring and for when a product goes to market. So we welcome you, ma'am.
Thank you very
Over
much.
to you, ma'am.
Good afternoon to all. Today, I'm going to present one brief presentation regarding testing and quality control of plastic product. First of all of you know that what is the meaning of plastic, or why the testing is required for plastic, and what is the need of quality control of plastic product. Till date, you know that what is the meaning of plastic, what is the meaning of polymer. Now I am going to represent you about the testing. What is the meaning of testing? Testing is an integral part of research and development, product design and manufacturing. Means, suppose you have this product, okay, you want to manufacture this product. So what you have to do? First, you have to identify the product. You have to research the product, back history of this material, what material it is. Then after research, you have to develop, means you have to develop the design. What is the design as per your requirement you need? As per your requirement, you made the design, means drawing. After that, you make a mold of it, and after that you have manufactured the product. After manufacturing, what is the real fact? You have to do the testing. What is the whether the design is suitable or not, what are the different types of manufacturing defects is there or not, whether it is fit to use for the customer or not. That is called testing. Okay, and that after testing, if the quality of the product is good, then it will be called, we have control the product through the various processes of this line. Means we have researched accurately the product, after that design the product accurately, after that manufacturing the product, and after testing tells about all the history of the material. Next, what is the major reason of testing? Why is the need of testing? Making of design concept. Suppose we have make a design, but whenever we are this application, it is does not suits the application. That means design will failure. Some design failure will be there. That is the reason of testing. Base for reliability. Suppose we have the selling this product into the market. Okay, that between manufacturing and the customer there is a reliable point, means you are giving money to the manufacturer and you are purchasing. Okay, whether it is, if it is the product is not good, then you are not reliable next time to the manufacturing, you will automatically go to the other company. That is called reliability. Then protection against liability. So some liability is there whenever you manufacturing a product, some liabilities is there that you have to control. Then quality control, then meeting the standard and specification. What is the meaning of standard and what is the meaning of specification? Standard is a common language between the various laboratories, means if I am sitting in the laboratory and you are sitting in the different laboratories, with the help of a standard we are doing the testing. After testing, the result should be equal, because if we are taking the same brand name company, if the result will be will different, then the testing will be all in vain. That's why standard is a common language. It tells how you will go to, how you will do the testing. That is written on the standard only. And specification is that some specified value is written on the standard only. Suppose for PVC pipe, the density should be 1.40 to 1.46. If the this density falls under this value, then your product will be good. That is called specification. That specification need the testing. History of the new material. What is the history of the new material? What is the history of the previous material? For these only we are doing the testing to evaluate the competitor's product. Suppose one company is already manufacturing one product and you want to do you want to manufacture the same product with defined design. That's why we have to do the testing and for safety reason. Then what is the need of what is testing? From incoming raw material to finished product, it is called testing. Okay, and to what are the evaluation we do? We have to new or competitive materials or modification to a process. If we want to do any modification, so we are doing the testing. And the fitness for purpose of a material product and the process, we are doing the testing. What is the meaning of quality control? A system of maintaining standard in manufactured products by testing a sample of the output against the specification. Means if the product meets the specification, that is called quality control, whichever I have told earlier also. Then there are 6 steps to develop a quality control process. Set your quality standard. First, if we want to control the quality, then we have to follow these 6 steps. First, set your quality standard. We have to choose the particular standard, then decide which quality standard to focus on. Then create operational processes to deliver quality. Then review your results, get feedback, make improvement. Means first you want to select one standard, then you have to focus on that standard only. After that, one operational system, means how the testing will be going on, that you have to check. And after testing, you have to do the evaluation of your test results, whether any deviation is there or not between the results. After that, you have to take the feedbacks from your customer, and depending upon the feedback, you have to do the improvement. Then only your quality will be controlled. Same thing, quality control refers to a checks carried output by products by workers. Means we have to do the feedback and should work on it. After that, quality will be controlled. Standard is already, I have already told you that what is the meaning of standard and what is the meaning of specification. A specification is a detailed description of requirement, dimension and materials. Means in specification everything is written, what should be the density, what should be, as per their application different tests are selected. Suppose one PVC pipe, what is the application? for potable water supply. For potable water supply, what are the tests to be carried out? That tests are written on that particular standard only. You need not to decide what are the tests to be carried out on the PVC pipe. Okay, standard will tell you, and you have to do your own way. As per your standard, you have to do. As per your own way, you can't do anything. After testing, you have to match with the specification whether it is the testing results falls under the specification specified value or not. Then only we can tell that the quality of the pipe is good or bad. Then different are the standard organization is there who are making the different standards. Means ASTM. ASTM is American Society for Testing and Materials. Next is ISO, International Standard Organization. Bureau of Indian Standard. This is an Indian standard as per the Indian atmosphere. They have made the standard only. Okay, and ASTM, ISO, IC all are the international standard. Then next we have to go, what are the different types of testing? There are two types of testing. One is micro testing and another is macro testing. What is micro testing? These are the micro testing. Identification of plastic density, determination of molecular weight, dilute solution viscosity, FTR analysis, NMR, DSCTG analysis. These all are micro testing analysis, because micro means you have to go inside, and after that you have to tell that what is the material is, what is the characteristics of the material, whether it is identification of material means you have to identify the material, you have to tell which material it is. And density, if we do the density test, then we can also say the what is the material is. Then molecular weight, obvious thing, all are related to your polymer characteristics only. From that part we can say what is the material, but what is the polymer is used to manufacturing the product. See, in identification test, there are different steps are there, which we will show you in your testing department. If we want to do the identification test, there are following steps are there. First, you have to see the material visually, whether it is first you have to see the visually whether it is transparent or translucent in color. If the material is transparent in color, then the material will be thermoplastic. If the material is translucent in color, then the material will be thermosetting plastic. From that part we can say whether it is thermoplastic or thermosetting. But after manufacturing a product, we can't say, because this is in dark in color, we can't recognize whether it is thermoplastic or thermosetting plastic. But next step is penetration of an hot rod. If we heat a rod and after that we will penetrate on it, then if it is thermoplastic, it will easily go inside. If it is not thermoplastic, it will not go inside. From that part we can say whether it is the plastic is thermoplastic or thermosetting plastic. Next is our method of fabrication, means in by which procedure the material is manufactured, whether it is injection molded, either it is extrusion molded, or it is blow molded, or transfer or compression. From that part we can also say whether the material is thermoplastic or thermosetting plastic. Next, after if we got the it is thermoplastic material, then we have to cut one small piece of sample and we have to put into the water. If it is floats in the water, then the material will be PP, either PP or PE material. PP means polypropylene, PE means polyethylene material. Next, if it sink in the water, then it will be other than P and PP. From that identification, directly visually we can say what kind of material it is. Next, we have to do the burning testing. It is very, very important testing. Then in the burning testing, we have to see how the burning is occurs. What are the color of burning? After burning, whether it is given a smoke or not, whether it is black smoke is evolving or not, and what is the smell of that smoke. That from that only we can say the material will be what material it will be. After that, from that we can suppose we got the material is PVC material. We have to take the next, we have to go to the solubility test. We have to take a small piece and we have to take the particular solvent of that material only. After that, we have to see whether the material is dissolving or not in that particular solvent. If it is dissolved, then we can say the material is this. Okay, this is the simple identification method. And besides this also, there are different types of identification of method also, by determining the density, by determining the FTIR, by determining the melting point. All are these tests are there. We can say this, yes, the material confirms the material is, whether it is PVC, whether it is PE, whether it is PP. Okay, from this particular test only we can confirm the material. But before density, FTIR and melting point, we can't confirm. We have to say it is maybe this material. Okay, this is the simple identification method of the plastic material. And next, our test is, there are different types of test is there in the plastic material. Means mechanical testing there, thermal testing is there, electrical is there, optical is there, permanence is there, rheological is there, flammability is there. Mechanical means what? We have to do the different types of mechanical test, means tensile, where strength of the material is determining, is called mechanical testing. Means whether the we have to do the tensile testing, whether compression, otherwise flexural testing, or shear. From that we can do the mechanical testing of the plastic material. Impact also there, in impact, isod impact, charpy impact, tensile impact, these all are the mechanical testing is there. Then my next slide is, what is the means of tensile strength? Tensile strength, maximum force divided by cross sectional area. If we pull a sample, then maximum, what is the maximum strength is coming, and we have to divide it by the cross sectional area, means length into thickness into width. By that only we can determine the what is the tensile strength of the particular material. Then elongation, how much elongate before breaking, it is called elongation at break. ভিডিও আছে ভিডিওটি দেখতে একটু ভিডিও ভিডিওটি এক্সট্রাকে তাই দেখুন। There some video is there. With the help of this video presentation, you can betterly understand. That's why I want to show you the video presentation of the tensile testing, how the tensile test is to be carried out. One video presentation is there. That part we also show in the testing department also, but if we see here, then it will be more helpful for you. তাতে আসলে এই ভিডিওটো Please see all of you how the tensile test to be carried out. This machine is called UTM, Universal Testing Machine, and these are the two jaws are there where we are testing the sample. The sound of- This is fixed for to measure the elongation of the machine. There are two parts of the machine. This is called fixed part, this is called movable part, and this is used to measure the elongation, how much elongation will be occurred during braking. That part we measure. Testing is going on. Graphical presentation is there. In that graphical maximum force is there. By cross-section area, got the tensile strength of that particular metal. Okay, like that only we also show the compressive and flexural strength. In compressive strength, how much maximum compressive force is required to compress the specimen? It is called compressive strength. This is a hollow product and is compressive. How much maximum force is required to compress the completely break the specimen? That is called compressive strength. Why it is required? Because आप नहीं दिए वो स्टैंडर्ड What is the application of this testing? Nowadays, the packaging is going on automatically, not manually. Okay, because one bottle is the automatic machines are there. In the automatic machine, some automatic feeder are there. Because from this point to this point, it will go by air, by the pressure of air. Okay, and it will be feed also with the pressure of air only. Then one pressure will be created in that bottle only, in that particular area. If the pressure will be more than this bottle will be break, then in this system of refilling of this process, there some disturbance of there, and there will be some loss will be there. So for that reason only, before filling the bottle, we are do the compressive strength to know the what will be the maximum force it will be bear during filling. Okay. Who says this? This is the machine configuration. Okay. One, it is minus, it is showing that it is coming down. First one will be that one, and what it is mm means this is area. This actually as per the machine requirement it will come. Different machine is there and different specification will be there. That's why it is coming in the two screen only. I'm not getting this point. That's why I'm not able to answer your question. Otherwise, I can tell. Main funda of this test is two plates will be there. And we have to put the sample here. How much maximum compressive strength is there required? That is we are calculating in this particular test. It's example. Now our next test is flexural modulus or flexural strength we are calculating in this process only. A bending resistance, bending force, all you can say. This is called 3-point bending system. This is called 3-point. This is called 4-point bending system. First, we have to take the thickness and width of the material. Depending on this, the flexural strength will come. This is called 3-point bending system because there 3 points are there. What is the maximum force required to bend the specimen and what is the flexibility of the specimen? We are determining this particular specimen. This is the indentation and how much it is coming in the how much bending is there. If you identify this point only. Indicator. All the facilities are there in our testing department. We'll show you briefly. Okay, just have a look, have an idea. That's why I'm showing here only. Three loading noses are there and pressure is coming from the load cell. And what is the maximum force is required? That is calculated. These all about the mechanical testing of the plastic material. Like that way, there are different types of tests are there. Means thermal testing means SDT VSP is there. all other tests is there. Then if optical property, opacity, haze, transparency, these tests are there. In case of rheological properties, MFI and viscosity, these all the rheological property of the plastic material. Like that way we are doing the testing. And like that way, these all are the different types of testing are to be carried out for the plastic material. Now I'm going on the last slide to you regarding how the inspection is carried out from a company from the whole lot. Suppose in our department, what is coming? Suppose one party is taking some pipes of the pipes or any product, some quantity, then they are sending to us. But we have to do the testing on site. During manufacturing only, we have to do the inspection. How the inspection is carried out, how the sample is to be taken from the lot, that is shown in this slide only. Please see. After that, we will go to the testing laboratory and we'll see all the facilities of our testing department.
So you are getting the glimpse of the inspection, how big inspection is carried out. So now you are so different types of for inspection. There are different types of as per inspection. We have to do HDP pipes in market. HDP pipes, PVC pipes, water storage tank, everything is available. But for which product we will do the inspection? Because the pipes for the pipes PVC and HDP. So we are giving you the video of HDP pipe inspection of HDP pipe that is done as per IS 4984 2016. So you can have the glimpse and all the documents is showing what kind of documents are required for that inspection. Means in that industry they are manufacturing the what ma'am have told before that we are doing the testing in our testing department. But during that inspection, the inspectors has to go to the manufacturing industry where the pipes are produced. There we have to do the on-site testing. Means the products will take that as per sampling. We have to take the sample as per means they have as a lot, they have stack. That we have to select them from as a sampling. We'll carry sample them and as per their dimension. All are given in the in IS 4984 in all the BS IS standards. All the sampling criteria is given. Means how much it has the dimension. As per that dimension, how much pipes we have to take for sampling. Then as per the sampling, the inspector will carry out the sampling. And after sampling the products, then he will have to give the some. There are in IS 4985 two types of tests are there: acceptance test and type test. For acceptance test means they are that the time duration is less. And for the type test, it goes for 42 days. So for inspection, we can't wait for 42 days. Na? Means some manufacturer will, after that inspection, after that inspection report, the inspector will give their products okay. It is okay or not. After their reporting, successful reporting, then only they can give the sample to the market. So for that, they have to take the acceptance test. Inspector will do the acceptance test for minimum up to 2 days. So in 4984, the inspection goes for 2 days. So that is acceptable. So there are various acceptance tests you can have. You are saying that, see, in the video you had, what I have told that as per sampling, how much sampling have to do, scale of sampling for dimensional requirements. See, lot size up to 150 sample, how much sample we have to take, acceptance number, rejection number, means how much sampling we have to do, how much testing we have to do, and means in every test, acceptance test, there are variety of tests. After this test, how much the tests are okay, how much it can be rejected, it is given. That is scale of sampling. Means out of 5, we'll test. If out of 5, I'm just giving you an example. Out of 5, if four pipes have failed in the test, so we have to reject it. So this is giving you scale of sampling. See the video. This is given what kind of visual inspection we have to do, that what they have to write in their pipes. Their batch number, their trade number, manufacturing date of manufacturing, in which shift they have manufactured, everything. Manufacturer name and trademark. See, all these are acceptance tests. What I have told you, all these are acceptance tests. Visual appearance is the first test, MFI, then density, then reversion, elongation and break, TBC, see, for dimension, what are the parameters? Mean outside diameter, wall thickness, ovality, length of the pipes, and coiling. Mean outside diameter is that all are the dimension of the pipe. It is okay, means for every testing, everything is plus minus is there. So it will go as per plus or minus. It will coming or not. It is giving in the coming in the range or not, that we have to check. See, visual inspection for color strips and marking. See, HDP pipes, from the video you can identify, you have seen this pipe, seen or not? HDP pipes, black color pipe with blue color marking. See, for this blue color also, the dimension is required. Means it cannot go up to above 3 mm. All our dimension are there. So for test inspection, the inspectors have to check all these things. This is the test is done for MA5, melt flow index or melt flow rate. Means for the pipes are manufactured by. Have you got the class of so have you got the class of processing now? You can understand the blow molding or the extrusion. Huh? So actually, pipes are manufactured from extrusion process. So for this, the material is extrusion graded or not. We have to check that by that MA5 test. This is the density. This is the test for reversion. Means 200 mm pipe we have to take from them, 100 mm marking we have to do, and we have to put it in hot air oven for 110 degrees centigrade for 1 hour. After 1 hour, how much the marking, you are seeing the video, no? That marking will suppress or extend, means the dimension is extends or suppress, that we have to check. That is the reversion. And elongation at break. This is before that you have got the idea of tensile strength. This is the same test, elongation, tensile strength and elongation. But we are seeing the elongation at break, means how much the pipe will elongate and at how much force the pipe will break. And this is CBC test. CBC means carbon black test. In the STTP pipe, all are black color. Black color means the raw material is not black actually. For oxidate, the pipe is kept in outside. The pipes are used in outside. So it will need some UV resistance. For that UV guard, that carbon black is given for manufacturing. So how much carbon black is given? It is also specified. It cannot go. It has to be in the range of 2 to 3%. So we have to check that also. And that for carbon black content is 2 to 3%, and it cannot, and the dispersion should also be uniform. Means in one side it cannot be black, another side it is blank. It should be equally distributed. So for that dispersion check, we have to do it in microscope. Another one test is oxygen index, and another is hydrostatic, means for the pipes. The pipes are mainly used for that. HDP pipe is used mainly for, it is for potable water supply, means water will come to the pipe. So how much pressure it will exert, it can exhibit, means the pipe can withstand how much pressure. So we have to check it, means how much pressure it can go, and that you have seen the pressure pressure rating of the pipe. So why it is given, means it can withstand this much of pressure. For the hydrostatic pressure means it is seeing its shelf life, means in longevity, how much longevity it will go. So all this test we have to do for the inspection, that in the industry for 2 days. After 2 days, we can conclude the inspection by giving them our acceptance or rejected report. So this is the conclusion of inspection.
Thank you very much. We'll go to the testing department. After that, we'll have a look how the testing is going on. For the 5 to 10 minutes, we'll take there. Okay. And what is the machinery is available in our testing laboratories? You just have a look.
Thank you very much, Mitali ma'am and Haimanti ma'am, for such an wonderful session. Because this session is very practical, and almost all of us are not familiar how this inspection is, how a product comes to the market after passing the inspection. So thank you very much for this wonderful session. And now the session is open for interaction. If anyone has any questions to ask to ma'am, then online participants, you can raise your hand, and offline participants, you can ask ma'am.
Dr. Anupama Rasput.
Anupama Rasput ma'am has some questions we have sent. Yes, ma'am.
Yes, ma'am. A very informative session by the ma'am. My question is that there are so many plastic product or plastic material in the form of lunch we are using in our lunch box, or daily use in plastic material also. And we are also when we heat our food product in a plastic lunch box, and so how can we check it's microwavable or not?
Thank you, ma'am, for your question. These carbon is generally used. Carbon, what is the purpose of use of carbon? It is protect the UV radiation. That's why we are using in the plastic pipes, and the quantity also written in the standard is also, it should be 2 to 3% should be used in that particular pipe only. If we mix that, it is no need to mix in the tiffin box or any other product, because tiffin box is very small area, and in the pipe is very large area. And in the if we say this, how we'll check? We'll do by migration test only, because in the pipe sample we have to do the migration test also. If the overall migration exceeds more than 60 ppl, then the product is not suitable for our health also. That particular test explain the carbon should be, how much carbon should be used on that particular material, and whether it is littering our food products or not, it is itself expellable. Thank you, ma'am.
Okay, ma'am, thank you.
Is there any more questions? You want to ask? So thank you very much, Mitali ma'am and Haimanti ma'am, for such an wonderful session. And we thank you for spending your valuable time with us. And I am sure all the participants got very much benefited from this session. And now this lecture session is over. And for the offline participants, there will be a live demonstration of the testing facilities available at CIPET CSTS-GUWAHATI. So we will proceed for that. And now we will proceed for the live demonstration part for the testing department. So all the online participants, you can leave the meeting because after lunch we will have a visit to our another center of plastic waste management center of CIPET CSTS Guwahati. So tomorrow morning we will meet again at 10 a.m. We have a lecture on advanced processing techniques by Praveen Basav sir, Joint Director of Ranchi. So we will meet again for the lecture series tomorrow at 10 a.m. morning. Thank you so much. Now, offline participants, please proceed for the live demonstration of the testing department. Thank you so much. Thank you so much.